Alright, today I'm going to be completing part C of homework 1 for separations. We've got a whole lot to tackle today, and most of it is going to be in CoLab. But there is a little bit of derivation that we've got to do that has to do with the first part of part C. So what we need to do today is explain and derive the expressions for the bubble and dew temperature and pressure so that when we go into CoLab, we know what we're coding up, we know our expressions. So to find these expressions, we're going to need to look at Raoult's law. Which we know is gamma I xi pi sat equals yi p. Now, since we're going to be dealing with a ideal binary mixture, this gamma I is just going to equal 1. So we can functionally get that out of our expression. Now moving on from here, we're going to do the easiest expression in my opinion, which is the bubble pressure. So starting over here, looking at Raoult's law, we can go ahead and add up each side to find our bubble pressure. What this yields the sigma xi pi sat equals sigma yi p. Now, we can go ahead and pull this p out of our expression because it's the total pressure. It is going to remain constant. And then, all we have left in this summation is our yi, and we know the summation of all of the vapor fractions is just going to equal 1. So, that leaves us a fairly simple equation for our bubble pressure, which is our bubble pressure is going to equal the summation of xi ei sat. So, it's 1 down. Now we're going to move on to the second easiest to derive here. We're going to do our dew pressure. And yet again, we're going to start with our Raoult's law, our xi pi sat equals yi p. And then this time around, before we put that summation there, we're going to go ahead and move our pi sat to the other side here for simplicity, which will give us xi equals yi p over pi sat. So now we can go ahead and put our summation in there on either side. And of course, we know that our xi alone, being summed up, is also just going to equal 1. And then, yet again, we can pull our p out of the summation, stick it right out there, and then we can put this entire summation divided to the other side, which yields our dew pressure, which is going to be equal to 1 over the summation of yi over pi sat. So now, we've got our bubble pressure and our dew pressure expressions derived right here. Now here's the tricky part, is finding our bubble temperature and dew temperature. As to ask us to derive equations for that is kind of a trick question. So over here, I'm just going to write temperature. Now, as you can see in Raoult's law, we don't have any kind of expression for temperature in here. That's because our temperature is hidden inside of our PI set. As in, our saturation vapor pressure for a given component is a function of the temperature. So we can't actually do any derivation on the board here. What we're going to need to do is find an expression for our temperature, such as the Clausius-Clapeyron, the Antoine equation, and I'm sure there's several more out there that can do it even more accurately than that. We're going to need to take one of those equations, and we're going to need to find the root temperature of our saturation vapor pressure equation, whether that be the Antoine, the Clausius-Clapeyron, or so on. Once we find that root, that is going to yield us our bubble and our dew temperature. So now, why don't we go ahead and move into Colab so that we can code up to find our bubble pressures, our dew pressures, and especially our bubble and dew temperatures.
Alrighty, I'm going to go ahead and get started with the coding portion of my separations homework part C. So to get started here, I've already imported the CHE5 tools that we're going to need for this coding, and I went ahead and defined our components. So I did our P equals props for benzene and toluene, which are going to be our two components we're going to be dealing with today. So to get started here, I'm going to go ahead and define our bubble P as a function of our liquid composition and our temperature. Going on from there, I'm going to say Yp, that is the gas composition times the pressure, and the gas composition we had found to be 1, is going to equal our X times our P dot Pvap at our given T. And that P dot Pvap is just going to give us our saturation vapor pressure at that T from our chem tools. Moving on from there, to get our pressure, as we defined up on the board, we are just going to sum all of our YPs. So we're going to do MP dot sum YP. And then we're just going to go ahead and return our P as well as our YP over P, a value that should be 1 if we've done everything right. Moving on from there, we're going to go ahead and do our dew pressure. So we're going to define our dew P as a function of Y this time and T. And as we set up above, our Pvap is going to equal our P dot Pvap of T. And going on farther from there, we can say that our pressure is going to equal 1 over MP dot sum of our Y. Look up at the equation. Yep, it's our Y over our Pvap. Fantastic. And then from there, we are just going to return, yet again, our P. And in order to get that check value, that one that we're supposed to get, I believe we're going to need to multiply our P. We're going to need to do, let me look up at our equation here, our pressure times our Y over our Pvap. Perfect. And that should return everything we need there. And now we can go ahead and move on to the temperatures. All right, now that we've got our bubble P and our dew P, we're going to go ahead and find our bubble t. So to find our bubble t, we're going to define our bubble t as a function of x and p this time. And then, since we're going to be finding the root of an equation to find our t, we're going to need to supply the root finder for an initial guess. And a really good initial guess for this case is going to be our t naught is going to equal mp dot sum our x times our p dot tb, that is finding our boiling point based off of our pressure. That's going to supply us with a really good guess for our root finder. So moving on to the root function itself, we're going to define f root as a function of t, and then we're just going to return the bubble p at x and t, the first value, because that's the actual pressure value, minus the pressure provided. And that is what we're trying to root out there. We're trying to get that to be zero, our p minus, or our bubble p minus our p. When that is zero, we have found the root temperature. So going on from here, we can go ahead and find our root t using scipy dot optimize dot root scalar. And then we're going to put in our root function our initial guess, our x naught equals t naught. We're going to say dot root. And then from this, finally, we are going, nope, not root scalar. We're going to return our t and our x times our p dot pvap at our t divided by p. And there we have our bubble t, which means that we can go ahead and move on to our due t, which is going to be very similar. So we're going to define our due t as a function of y and p. Yet again, we're going to supply our initial guess as a p dot sum of, this time, y times p dot tb rp. Yet again, we are going to, not quite done yet. We're going to define our f root as a function of t, and we're going to return the due p at our y and rt minus rp, yet again finding that where that value is 0. Press enter. Hold on. Got a colon here. And now we can find our t to be scipy dot optimize dot root scalar f root with our x naught, our initial value, guess being our t naught that we described up here, and we are going to do the scalar method, which I actually need to put in up here. And there we have all 4 of our functions. We got our bubble p, our due p, our bubble t, and our due t. One last note before we move on to the next portion of this. I realize I made a mistake here. Should not be scalar, it should be secant. I was getting my root scalar and my method secant a little confused there. But now we should be all good. Alrighty, now that we have all of our bubble P, do P, bubble T, and do T, we can go ahead and look at the next part of our problem, which is going to be to create a VLE diagram for an ideal binary mixture with a constant temperature of 360 Kelvin. So to do this, we're going to go ahead and set our temperature equal to 360K. And then we need to create our X values. So our X's, say X1s, are going to be equal to mp.lin space, going from 0 to 1 with 21 values in between. And then we're going to create an empty array for our p values. So our p's are going to equal empty set of brackets, and then our y1s are also going to equal an empty set of brackets. For now, we're going to fill those up as we go, obviously. And moving on, we're going to say for x1 in x's, x1s, we're going, oops, colon there. We're going to have our p and our y equal to bubble p, then mp.array of our x1 value and r1 minus x1 or x2 and our temperature. And then we're going to do p's dot, and with these new p values, we're going to do y's dot append with our new y values. That's going to be the first value there. And now I think we're good to go ahead and create our plots. We're going to do fig equal make subplots. We're going to do figure dot add scatter do x equal to our x1s, all of our liquid composition values, our y's equal to our p's, our pressure values. We're going to do mode equal lines. And finally, we're going to name this, and this is going to be our bubble P line on our VLA diagram. Moving on, we're going to do figure dot add scatter. Have our x's be our y's this time, our y1s. Our y's are still going to be our p's. Our mode is going to be lines. We're going to name this our dew pressure. All right. Now, let's just see how this looks. Hold on. What's our problem? I see. Alrighty. Sorry, got a little bit lost there. We have a couple little mistakes in there, but no problem. Alrighty, look at that. Beautiful. So you can see here, we've got our bubble pressure up above here, our dew pressure below. Now that we've got our constant temperature VLE diagram, we're going to go ahead and do our constant pressure VLE diagram. So I'll go ahead and label this as a constant pressure VLE. And that constant pressure is going to be equal to 1E5 pascals. And then we're pretty much going to do the same exact thing that we've done up here. So we're going to create our x's. You see our x1s are going to equal to numpy.lin space from 0 to 1 with 21 points in between. And then we're going to create our empty arrays for our t's this time, not our p's. And our y1s yet again. And then we're going to say for x1 in x1s, we're going to say that t and y is going to this time equal our bubble T instead of our bubble P. Everything's a little bit reversed here. So say our bubble T, our MP dot array from yet again our x1 to our 1 minus x1 or x2. And this time we're looking for our P. All right. And then yet again, we're going to append our arrays. Say y1s are y at first position. And then yet again, we are going to do figure equals make subplots. We're going to do figure dot add scatter our x equal to our x1s, our y equal to our temperatures, our mode equal lines, our name is going to be our bubble T. And then we're going to do the exact same thing down here. But for our due T, so our x is going to equal our y1s, y is going to equal our temperatures, our mode is lines, and our name is going to be due P. Fantastic. What am I doing? All right, so I just realized we ran into a little bit of trouble just from a little typo up here. Need to put SP, not SciPy, up there. And then we should be able to do figure dot date layout, and we can do template equals flatly dark. Fantastic. All right, here we go. This is our VLE diagram for our constant pressure. So you can see here we've got our bubble T and our due T switched over as compared to this one. So it looks like this is all worked. We've gotten our VLE plots. All right, for the final step of our part C, we are going to generate an XY plot for our benzene toluene mixture at 1 bar. So to do that, we don't even need to enter any data. We can just do our figure equals make subplots. And then we can add scatter. And all we are going to add to this is our x equals our x1s, our y's equal our y1s. And we're going to do mode equals markers, as these are points. We're going to do figure dot add scatter. We're going to have our x equal just from 0 to 1, because we're just kind of creating like a straight line to compare our XY plot to. Go from Y from 0 to 1. We're going to have the mode for this is just going to be lines. And you know what? The AI is right. You can never hurt to have flatly dark. Alrighty, so look at that. We can see our straight line. And we can see that our vapor liquid equilibrium follows this curve up here. And I think that is the end of homework 1 part C for separations.